Hello everyone. Right now we are going to start with module number 1. So let's start with the module number 1 where we are going to discuss very basics of statistics. Our objective here is to understand the data types and what are the different types of data that will be available with us. And in fact, if you go and talk to data scientists or if you get any chance to read articles related to data analysis and statistics, you will see all these jargons are used pretty heavily. So we're trying to explore what different kinds of data are available with us. How can we broadly classify the data into different types? And then we'll go into further analysis of different data that we are going to classify under quantitative and qualitative category. Then we'll try to define what is population and sample, because these are the two terms that you are going to use very frequently throughout this whole course. And in fact, not in this course, whenever you get a chance to explore more into the statistic world, or if you did get a chance, or if you already had a chance to explore all those areas, you might have already seen the usage of population sample so frequently. So we are going to discuss what exactly is sample and what is population. How can we make sample represent the whole population? Then as we are proceeding, we'll try to see what are the techniques, or is it only the blind way that we are taking a sample out of a population, or is there any logic behind that? So all these things we are going to cover in topic number 3, where we are going to discuss understanding sampling techniques. And then at the end, we'll see some of the techniques in order to represent the data. We are going to cover the confusion matrix. How can we represent the data in confusion matrix to actually understand the whole model and how it is behaving? So let's start. So first of all, the question is, what exactly is data? So if you go by the definition, the data is nothing but, in general terms, refers to the fact and statistics collected together for reference or analysis. So those facts and statistics may vary as per the organization or as per the field that you're talking about. It may be data related to banking systems, financial systems. The data may be related to any of the other varied areas. That may be any kind of research related data. That can be any of the general data related to the population of a country, things like that. So it can be any facts. And when we take all those facts for any kind of reference, or that's been shared for some kind of analysis in order to come up with some kind of a result, then we term that whole collection of facts as data. So if I'm talking about those facts and data, or those facts or figures or statistics, can I have different types of facts and different types of statistics? Let's see. So we broadly classify the data into two types. We call it as qualitative data and quantitative data. If you go by the meaning of this term, data, you will see qualitative tilted more towards where we don't have any of the numerical stuff, or we have the properties or the characteristic of the data available with us. That is characteristics or descriptors, those that cannot be easily measured, but can be observed subjectively, such as smell or taste or textures. So all of these kind of things comes under qualitative data. Second category is quantitative data, where, as the name suggests, we are talking about something measurable, because we're talking about in terms of quantity. So quantitative data deals with numbers, things you can measure, dimensions such as height, width, length, temperature of room, temperature of a country, temperature of an area, humidity, like that. So further, if you go into detail of qualitative, you can broadly divide qualitative data into two types. One is called nominal data, another is called ordinal data. So if you talk about nominal data, so as the name suggests, it represents some kind of characteristic. Let's say if you're talking about gender of a population or of a race, then we can say that the gender can be of male or female. You can say name or characteristic that data represents. It is sometimes called as categorical data as well, that has one or more categories, but there is no intrinsic ordering to the categories that you can see here. There is no ordering. It doesn't matter whether male comes before, females come after male, or before male. It doesn't matter. The ordering here doesn't matter. So these kinds of data is called as nominal data. So if you try to understand this, the same example with the help of R, you will see that it all depends on what kind of input is entered by the user. Let's say, for example, it's being prompted to enter input number 1. So that is being assigned to answer number 1. And again, the input is being assigned to answer 2. We have taken two variables and we are just putting a check. If you have placed as yes to the answers, then we can simply say print a message that welcome to the girls club. Other than that, then you just print a message saying, sorry boys, you cannot join the club. So all of these results or the print statements are executed on the basis of the answer given by you, which is nothing but kind of a simple mentioning of any of the characteristic, or you can say just answers entered by the user. It's very trivial example to represent that what exactly is nominal data. When you say ordinal data, that means there is some kind of inherent order associated with that kind of data. So there is an ordering of the variables. Now, if you see this example here, we're talking about the customer IDs and a rating associated with those customers. So let's say we have customer ID number 1, which is having ID of 101, and the rating given to that particular customer is strongly agree. Similarly, 302 disagree, and similarly the other neutral agree and strongly disagree. So if you see, there is an inherent ordering is already in place there, and that ordering is starting with a very strongly agree, which is customer ID 101, till it goes to the another customer with the rating scale of strongly disagree. So there is an order, because strongly disagree one will be pretty much in low priority compared to the strongly agree one, or the neutral one will be somewhere in the middle. So the value which is associated with particular variable or with particular data having an inherent order is called as ordinal data. So if you want to take the example of ordinal data, it's pretty simple and straightforward. Here, if you talk about the marks, so the value of the marks has some inherent order, because the check that we have placed here is the value of the marks is less than 40, then that student is considered as failed. If it is between 40 and 50, then it's a second class. If it's between 50 and 60, that's a first class. And if it's more than 60 or equal to 60, then message is congratulations, you got a distinction. That means the value of marks has an inherent order, because if it is less than 40, then it has some different value and it has some different consequences. If it has something else between 40 and 50, it has something else, and respectively for other values it has some other significance. So because of the order present with the data, we call that particular kind of data as ordinal data. Let's go back to quantitative data now. So as I already told you, quantitative data is nothing but the data that we can measure, or the data that has some kind of quantity associated with that data. So the data that deals with numbers are broadly classified into quantitative data, and they further can be classified into two types. One is called as discrete data and the continuous data. When I say discrete data, that means the data that you can count, that has a specific defined value of it, that involves in integers. For example, we just saw about the mask. So how much marks you got is the discrete data. How many runs scored by a batsman is a discrete quantity that we can measure. Take a look at this example. We're talking about the data related to the mobile phone companies, and the mobile phone company is being represented by the column called organization, having Samsung, Apple, Nokia, LG, and Sony. And the number of the product given by those organization is being present in the column called number of products. So if you see, Samsung has a definite or discrete value of 500. Apple has a definite and discrete value of 30. So these kinds of data is called as discrete data, because we have a finite number of values possible with that particular data, or we can say product. You cannot further subdivide it. You cannot further change the units or something else, because that's a discrete quantity we are talking about. Unlike the same thing, when we talk about continuous data, that is also includes measurement, but that can be further divided, or you can say that can be further finer increments and modifications, or you can say further levels. Let's see here. If we're talking about the patient and the weight of the patient, then the weight of the patient is represented in the form of 86.5 kg. But the same weight can be represented in pounds as well. That can be further represented in the quantities of the grams and to whatever level. So we can further modify or reduce to any level we want. That kind of data is called as continuous data, which can be measured on a continuum or a scale. So why I'm telling you all this? Because based on these categories, whether you're talking about the discrete or the continuous, later on you will see we have a different distributions related to these kinds of data sets. When you talk about discrete data, you will later on see a binomial distribution is coming into the picture. Poisson's distribution is coming into the picture based on different representations of that data. Later on with the continuous data, you will see probability density function is coming into the picture. So different kinds of data normal distribution is coming into the picture. Different kinds of data projections, or you can say distributions, arise from these kinds of data. It's important to at least understand the meaning behind all these kinds of different jargons. So apart from the data, now we are talking about variables. And we all know in the mathematics, we have an habit of taking variables, right? If you wanted to solve any of the equation, let's say y equals to mx plus c, then you have y and x as two variables. So it is nothing but it represents an unknown value or a value that varies. That's called as variable. The variable can be further divided into so many categories. It's like categorical variable, control variable, independent variable, confounding variable, and dependent variable. So when we talk about categorical variable, that means it fits in some kind of a category and does not have a numerical value associated with it. It is unlike a normal variable that we normally see in mathematics, right? Because in mathematics, we normally define a variable, say, for example, x, and we assign a numerical value for it. But unlike that, we have a different categorical variable that holds a kind of a non-numerical value. And let's say when we are talking about the categorical variable, that value can be of English type, or let's say if we're talking about values associated with the college subjects, then we can store those values in variables, values like English, mathematics, and political science. That value is stored in a variable, and that variable is called as categorical variable. Then after that, we have another variable called control variable. A control variable is a variable which is meant to be kept constant. Now, why it is meant to be kept constant? Let's say, for example, if you're talking about growth of the plants in a simulator, or we can say controlled environment, because most of the experiments or the research, they're all being done in a controlled or a regulated environment. Now, why we need to do that is because whatever the figures or whatever the research analysis that will be proposed at the end shouldn't be varied based on some external effects or external quantities. Right. So we need to make some of the things constant. Let's say, for example, if you are trying to measure the growth of the plants in a simulated environment, so let's say you can keep the amount of sunlight as a constant variable, or you can say control variable. Because if you keep on varying the sunlight, then what kind of analysis, whatever analysis that you're doing on your plants, that may has some of the varied effects. Right? And those variables are called as control variables. Then you have independent variables, variables which is changed by the researchers or the person who is doing all that research or analysis, called as independent variable. For example, if you're investigating how changes in size of water faucet, of amount of water flow, the faucet size is your independent variable, and you have no control over the amount of water which is flowing. Or let's say, for example, if you're trying to measure, let's say a very simple example, if you're trying to measure the length of a wave versus the time in a day. So the time in a day is your independent variable because you have no control over that, right? But that time has very significant effect on the output of your whole analysis of getting the relationship between the time and the height of the waves. So the height of the waves is your dependent variable, and the time that we are talking about is your independent variable. That is how we further classify into two categories, independent and dependent. Then we have one more quantity, or you can say one more type of variable called confounding variable. In order to understand confounding variable, let's take an example. Let's say we have 200 volunteers. Out of those 200 volunteers, we have 100 as men and 100 as women. That the lack of exercise basically leads to weight gain. But we are only considering one variable here, lack of exercise. What about how much you eat? We are not taking into consideration that. Or when you're talking about volunteers, we have 100 women and 100 men. There's one more saying that men can eat more than women. We are not taking into consideration that fact, or you can say that point. So nothing was mentioned about starting weight. Nothing was mentioned about the occupation. Nothing was mentioned about the age. So these are called as your confounding variables. Because here men can eat more than a woman, so his sex can be a confounding variable again. And we are not taking into consideration all the other factors that may lead to significant changes in the output of your whole exercise or analysis. So those kinds of variables are called as confounding variables. Let's take a look at a simple experimental research example. Now here, in this experimental research, the aim is to manipulate an independent variable and then examine the effect that this change has on dependent variables. Let's say there are 100 students completing a math exam where the dependent variable was the exam marks and the independent variable were revision time and intelligence. Now, if you try to relate the revision time and IQ with the exam score, you will see a linear relationship between these two variables. That means the more the revision time, the better the exam score. The less the revision time, the less the exam score. So what they have done, they have divided the group. There are 100 students and the group is divided into two. One is having 50, another is having 50 students. And the instructions given to the group number one is that they have to revise for 20 hours, and the group two students shouldn't be allowed to do any revision. And then if you try to compare the results of these two, since we already know there is a linear relationship, then you will see how if you're varying this quantity, the result is getting affected. Giving you a result of analysis that how the dependent and independent variables changes the whole scenario. Another example is non-experimental research. In non-experimental, the researcher does not manipulate the independent variable. We're not changing the independent variable. This is not to say that it is impossible, but it will be impractical. Let's say the researcher who is interested in the effect of the illegal recreational drug use, which is the independent variable for your information in this case, on certain types of behavior. That means what is our objective? The dependent variable that is going to affect it with the inclusion or exclusion of the independent variable. It will be unethical to ask individuals to take illegal drugs in order to study what effect this had on certain behaviors. So this is kind of a non-experimental research. If you can modify, cannot modify the independent variable, that has its own effect on dependent variable. Now let's talk about the more technical sense of or technical jargons. And mostly we'll be talking about population and sample. So what exactly is population? So whenever you start with any kind of data analysis or any kind of analysis that you have to do on some kind of input sets, then whenever you get the whole data set for which you have to provide your analysis, let's say we are giving with the, say for example, last 10 years weather information of a particular region. And those last 10 years data can be huge data. So whatever input data given to us, and we need to come up with some kind of analysis, that whole data set is called as population. So normally speaking, you normally won't go and apply the whole analysis or whole mathematics on the whole population. The idea is to come up with some kind of a sample out of that population. So let's say if you have 10 million data set values, and in order to take sample out of it, you will start with 10,000 or maybe 1,000. But there is again a science behind how to get that 1,000 results, or how to get 1,000 results from the 10,000 data set points, that we call as sampling technique. So sample is nothing but some of the randomly chosen points, or you can say data sets from the whole population set. So the idea here is take the sample out of whole population, put in analysis on that sample, come up with the analysis results, and try to represent that analysis result on the whole population set. That is the whole idea behind sampling and population. So how to get that particular sample, because that sample shouldn't be biased, shouldn't be blindly chosen sample, because that blindly chosen sample may have some of the bias related terms which may affect the results, right? So we need to choose the sample pretty logically. So that is why we have sampling technique. So there are two types of sampling techniques available. One is called probability sampling, another is non-probability sampling. In probability sampling, it is basically based on the fact that each member of the population has a known or equal chances of being selected. When I'm saying selected, that means for becoming a part of the sample. So for example, if you had a population of 100 people, each people would have odds of 1 out of 100 of being chosen. So if you have to choose out of 100 people, so each and every individual has an equal and likely chances of getting chosen. That is what we call as probability sampling. Another is non-probability sampling. With the non-probability sampling, those odds are not equal. For example, a person might have a better chance of being chosen if they live close to a researcher or have access to computer. So there are some unforeseen circumstances that may actually affect the sampling of the data. Because I told you, if you want to choose a person out of 100 samples, so you might choose your neighbor before the other samples or the other people because of the closeness and other factors. That is called as non-sampling or non-probability sampling. Probability sampling can be further divided into three types. We call it as random sampling, systematic sampling, and stratified sampling. Random sampling is very basic sampling technique. In this one, we select a group of subjects for study from a very large group. And each individual is chosen entirely by chance, and each member of the population has an equal and likely chances of being included in the sample. That's what is a very basic sampling is in this as a first representation of your probability sampling, and we call it as random sampling. Another sampling is stratified sampling. In the stratified sampling, there may be some factors which divides the population into some population, like some kind of groups or stratum. The measurement of the interest may vary among the different subpopulations. A stratified sample is obtained by taking samples from each stratum or subgroup of the population. The proportion of each stratum in the sample should be same as in the population. That's what the logic behind. And it is being very frequently used when you have a population of heterogeneous records. When I say heterogeneous, that means mixed records are there. And we can let's see in this slide where we have divided the whole population into male subset and the female subset. So we subdivided into category based on subset. And then further, we can start with our random sampling again, the same part of stratified sampling as well. Systematic sampling is very, very simple sampling. In this one, what we'll do, we'll start with some kind of a repetitive technique. Say for example, we always start with taking into consideration every fourth record or every second record, right? So it's pretty simple. It's kind of a, you can say, ordered sampling we are doing here. That's why the name it is as systematic, because we have a particular system for that. So we need to take every second or fourth or sixth, whatever the record you have to take, and you have to keep on repeating the step again and again. That's called as systematic sampling. Now let's come back to non-probability sampling. So non-probability sampling, you can say it's not a product of randomized selection process. There's no randomized selection process included here. Here, the subjects are selected on the basis of their accessibility or by the purposive personal judgment of the researcher. Some of the external factor, there's no mathematics there. So basically, these kinds of sampling, we have a problem of sample representing the entire population is not confirmed. So therefore, they cannot be used in generalization of the entire population. So these kinds of techniques not that frequently used in order to generalize for the whole population. We can further divide non-probability sampling into 4 or 5 types. Sometimes you will see 4 different variations, and sometimes you see 5. So we broadly classify into convenience type, consecutive type, quota type, judgmental, and snowball. So what exactly is convenience non-probability sampling? So as the name suggests, the samples are taken based on the convenience of the researcher or the person who is doing that analysis. That is called as convenience sampling. Then we might have consecutive as well. So whatever the samples that you have available as a part of that particular process, you will include all those samples. We call it as consecutive. Then we have quota. In this one, we need to actually, the researcher ensures that equal or proportionate representation of the subjects depending on which trait is considered as basis of the quota. Let's say if you're talking about college students, so the college year level can be considered as your quota, so that we can divide into first year, second year, third year, fourth year, things like that. That is called as quota sampling. Then we have judgmental sampling. In judgmental, the researcher should be having a specific purpose in mind, where based on that specific purpose, some of them may be more deserving than the others, based on, let's say, whatever the samples we are taking. If we're talking about English speaking people, so the people who are native English speakers might be given favor compared to the other. Like so based on the judgment of the researcher or the analyst, you can include some of the samples. Then we have snowball. In this type of sampling, the researcher asks the initial subject to identify another potential subject who also meets the criteria. So that is called as snowball sampling. After that, we'll take another step in statistics where we'll talk about descriptive statistics. So when we talk about descriptive statistics, in descriptive statistics, we try to represent the data in the form of graphs or maybe some kind of different graphical formats, like maybe histograms, maybe line plots, line graphs, scatter plots, right? And based on that representation, we'll come up with, and that particular data being represented based on some kind of central tendency. Okay, means that particular graph might be representing distribution of the mean, might be representing distribution of the measures of the spread, right? So it all depends on what kind of data, what kind of analysis you are dealing with. So in order to do that, we have few of the measures of the center, or you can say central tendency. That measures are nothing but the mean, median, and mode. So when you talk about mean will give you basic central tendency about the whole group. Let's say if I'm talking about the average marks scored by each and every student in school A is 90%, then that particular data will give us a meaning, or you can say an information about the whole school, that on an average, each individual student of the school scores around 90%. So it gives us a central tendency that the school performs normally well. So like that, we have mean, we have median, we have mode data that can be used in different kinds of analysis in order to get the central tendency of the whole population. Okay. So if you try to understand the meaning of all those terms, let's take a look at this example. Here we have a sample data sets of empty cars containing the variables called cars, miles per gallon, cylinder, displacement, horsepower, and things like that. Okay. Now, one by one, we'll try to come up with these measures of the centers. And let's say if we, for example, we need to find out what is the average of the horsepower, how to find average of horsepower, how to find common type of cylinder, how to find center value among miles per gallon entries. So let's say start with an analysis number 1. Here we want to find out the most common type of cylinder. So when you say most common type of cylinder, and you see the value of the most common type of cylinder are divided into 2 types, like 4 and 6. And if you try to calculate the mean, which is nothing but taking the average out of the whole records. So coming back to the first analysis, we're talking about the most common type of cylinders. We got the 2 values like 4 and 6. So if you see, the frequency of 6 is more. So you can say, we can predict that, okay, most common type of cylinder is 6 cylinder. If you want to find out the average horsepower of the cars among the population of the cars, now in this case, we'll calculate the average, or you can say mean of all the values of the horsepower. So we'll get the average value of the horsepower in the whole sample population. Then let's say we need to find out the center value of the miles per gallon among the population of the cars. How to get the central value? We can get the central value with the help of median of the whole data set. which is nothing, but we'll try to take the 2 if the number of the entries are even, then we need to consider 2 entries. If it is odd, then we'll take the middle value. Okay, that's what they're doing here. Now, in order to represent the same thing in R, this can be done pretty easy. Let's take a quick example with the help of RStudio. If you try to see, we just have sample for mean. Let's see if we can do that. We take the sample, right? We got the sample. If you want to calculate the mean, it's a simple direct function is available. So we can directly create the mean like that. If you want to check the value of the mean, you can simply say the value of mean is this. Okay, right? You can see the mean is something around 10.14. So that is how you can actually calculate mean. That is how you can calculate the median. That is how you can calculate the mode. We have different functions written for that, right? If you try to see for mean, median, mode, you can see. So mean, we already know how to create. Median also direct function available. In order to get the mode value, which is nothing but the most frequent values present in the whole dataset points, we can define our own function in R with the help of like this. Get mode is the name of the function, and we can get the unique set of values. We can get the maximum of the occurrence of the values, and then the result will give us the mode of the whole data set. And we can actually represent the data set with the help of histogram. So in order to do that in R, you just have to use the function called hist and pass on the parameters. So that's how we can calculate the median in R. So direct function available. So if you go by the mathematical definition, you can see it's nothing but take the 2 values, middle values, and get the, if it is odd, then you can get the direct value. If it is even, you can have to take the 2 values and divide it by 2. Similarly, mean, take the sum of all the values divided by the number of the values, and mode is nothing but the number of the frequent, highly, or you can say the most frequent number. That's what they come as mode of the whole data set. Like measure of the center, we have another thing called measure of the spread, right? How can you measure the spread of the data? So there are 4 terminologies used there. One is called as range, one is called interquartile range, another is variance, another is standard deviation. So range, as the name suggests, it is giving you some kind of you can say, whole sort of values between 2 points like max and minimum. So if we take the difference between max and minimum, we ideally will get the value of the whole range, and that is called as range of values. So in some of the in some of the libraries, you will see there are direct functions available in order to get the value, maximum value of data set points, at the same time to get the minimum value. Once you take the difference between the maximum value and the minimum value, you'll get a whole spread of values, and we call it as range. Similar to the range, we have quartiles as well. So instead of getting the difference between max and minimum, we'll try to divide the whole data set into some kinds of quarters, and those are called as quartiles. If you see the slide, we have divided the set of 10 points into 3 quarters. Okay, that is how we can divide the whole set again in terms of quarters. If you see this example, we are again dividing into different quarters because we have 100 values. The quarters will be lying between 25th and 26th, 50 and 51st, and 75th and 76th. That's how we can calculate the quartiles. Now, there is another term called interquartile range. So range, we already know the difference between max and min. Interquartile range, as the name suggests, it's the distance between the quartiles, right? So say, for example, if you wanted to have a interquartile range between quarter 3 and 1, so we'll normally take quarter 3 value minus quarter 1 value. That will give you interquartile range. Apart from interquartile range, there are 2 more important terms. One is called as deviation, another is called as variance. So both of these terminologies revolves around the calculation of mean. So basically, they will tell us how much each data is varying from the mean, and we call it as variance. And difference between each value of the mean is called as deviation, and different, or you can say the deviations and entails computing square of deviation is called as variance. So basically, how it is being calculated is, since we need to calculate the variance of the whole data set or the whole population, so first of all, we need to calculate the difference between the set point and the mean value. And then one by one, we need to add for all the data sets points available. And then we need to square it so that we cannot cancel out the difference which may be assigned results, right? That's why we squared it. And then we took for the whole sample, divided by n-1 in the case of sample variance. Why sample variance n-1? Because later on you will see in some of the further classes there is a term called degree of freedom, and that degree of freedom we need to subtract from the number of the samples in order to get the exact value, in order to take into consideration you can say the units of error, you can say additional variability that may be missed if you take all the n samples. And then the population variance is nothing but the set of population and the population mean, and the same formula as it is for the sample variance. So as I told you, variance is a measure of the spread between numbers in a data set. It measures how far each number in the set is from mean. Similarly, for deviation is a measure or a dispersion of a set of data from its mean. So basically, variance is at an individual level, and the deviation is to the whole data set point. If the data set points are far from the mean, if they are very much far from the mean, then the deviation is very high. Let's take a look at this example in order to understand standard deviation. So say for example, Sam has 20 rose bushes. The number of the flowers on each bush is 9, 2, 5, 4, 12, 7, 8, and 11, and few other values. Now we need to calculate the standard deviation. So first of all, in order, as I told you, that standard deviation and sample variance revolves around the mean values. So first of all, we need to calculate the mean value. So here in this case, the mean value is 7. Then we need to calculate the difference of each point with the mean value, square it, and then sum it all. So that's what we are doing in this step. We are squaring each and individual value. Last step, we are summing it all. And then we are dividing with the n-1 sample or total sample. And then you will get a result that some mean the square difference is 8.9. And in order to get the standard deviation, you will get as 2.983 is the standard deviation of the whole data set. So in order to represent the same thing in R, we already saw, we take the sample values and then we create a histogram in order to represent that. So let's quickly run this example. Get the histogram. This is something like this histogram you will get. So this is the initial set histogram, then we calculate the mean value. In order to print the mean value, we'll print the mean variable, we'll get the mean value, we'll print the median value, and then we define the function for getting a mode value, okay? And then we store the value in the result function, result variable, and print directly of the mode, we'll get the mode values like this, right? So that's how we can actually do the same stuff of calculating mean, median, mode in R, okay? And at the same time, we can draw the graph as well. So in order to calculate the range, as I told you, right, most of the languages supports the calculation of maximum value and the minimum value to the whole data set point directly with the help of some of the APIs. So those APIs are max and min here in this case. So max data minus min data will give you a range. And if you wanted to calculate the variance of that value, just call a var function. It will give you the variance of the whole data set point. All right. So another important term in this course is information gain and entropy. So before we go into the details of information gain and entropy, first of all, we need to understand what is meant by purity or what is meant by impurity. So if you're from the scientific background, you might have heard this term called entropy in case of physics, where entropy is a measure of uncertainty in the data. So what this physics term is doing here? So this can be explained very beautifully with the help of one example. So let me explain you that example, and then we'll come to the formal definition of these terms. Let's see. I have a use case where a match is going to be played on specific days. The task is to forecast whether the match will be played or not according to the weather conditions. So we need to make a prediction here. And for that, we have a data set available with us, which is having like 14 values for each day. And that has few of the parameters like outlook, which may be sunny, overcast, rain. And we have humidity, which may be high, normal. And we may have wind, like strong wind, weak wind. And based on all these factors, whether we can play or not. So if you take a look at this one, there are total 9 yes and 5 no's. That means there are 9 outputs that suggest us that the play will happen, and there are 5 no that suggest the play won't happen. So based on the different properties of the outlook, we divided the set into 3 further divisions, right? Like sunny, overcast, and rain. Now you must be wondering, why did I choose only outlook, right? So let me answer that question shortly. Let's first try to understand what exactly is information gain and entropy I'm talking about. And then gradually you will understand where we can use entropy and information gain and why we have chosen only outlook as a end result feature to be taken, not humidity and wind. Let's imagine we somehow got to know that outlook has to be taken. So if you take outlook, we get 3 different results there. It may be outlook may be sunny, it may be overcast, and rain. So if we talk about outlook as sunny, you will get again 3 different results, or you can say 5 different results, where 2 of them are suggesting that play can happen and 3 are suggesting that play may not happen. Then if you go with overcast, all of the data set or all of the entries suggesting that play will happen. If you go with the rain, then there are 3 suggestions that play will happen and 2 suggestions play won't happen. Now, if you go into detail, this is an example taken from the decision tree algorithm, right? So if you see, initially we started with some kind of a mixed data. We don't have correct information available with us. Based on that, we can say the play will happen or not, because there is a mixed data. Because 9 years we started in 5 nodes. That kind of data we call as that has impurity, because there is no final resolution we can make on the basis of that value, those values like 9 years and 5 nodes. Similarly, if you take sunny data, there is the same problem with this one because there are 2 years and 3 nodes. Similarly, if you take the rain, the same problem is there as well with 3 years and 2. But if you take the overcast is completely pure data. When I say completely pure data, that means there is no chances of confusion here, and you can blindly go and say, okay, the play will happen. That kind of data is called as pure data. Now, if you think, how can you calculate the entropy or a disturbance? That is a very simple formula where we try to calculate the probability of getting those values. So the probability of getting yes and probability of getting no, we divide with all those terminology, simple mathematical formulas there. And once you get, so it will give you a total entropy for that combination, which is 0.94, which is very high. So based on all this calculation, so if you go back to the formula, if you see the same formula we have applied there. So as I told you, it is a measure of uncertainty. And in fact, based on the value of entropy, you can calculate the information gain. Now, if you see in this example, we have started with the entropy of 0.94. We have just calculated. So here we have, you can say, I'll just represent entropy with E. So here we have entropy of 0.94, right? Okay, and if you see here, we have pure data set. So we have 100% information gain here. So how can 100% information gain, which is nothing but Ig, some value of entropy, and minus something, other value of entropy. Here, we don't have any entropy value because the number of nodes is 0 here, right? So we'll probably get 0 value. But here, if you see, if you calculate the entropy here, you will get some value of entropy again. And then differentiating that initial value of entropy with this value of entropy, you will get some differences. That will give you the information gain value. So I'll show you shortly. Just now, why I told you all this about information gain and this one. So ideally, we always want 100% information gain. We don't want to lose our data on the entropy values. So we need to choose a better one that will give a 100% information gain. We should not lose the data while taking decisions. So out of all the combination like sunny outlook, windy and humidity and other things, right? Why we have chosen outlook and that too with all these values, right? So if we'll start with calculating the information gain in each and every case. So information gain in case of windy, you can see here. So entropy for the initial set we all know, which is 9 years and 5 nodes, which is common to all of the combinations. We'll get the entropy of the initial system is 0.94, and then we calculate the entropy for the other combination that we are taking into account, right? So you'll see the difference information gain is 0.04, which is very less, right? So you want the more information gain. You go to the another combination, and here you will see 0.94 minus some other combination that we have taken for outlook, right? And you will see the here the difference of, or you can say the information gain that we're getting is 0.24, which is bigger compared to 0.048. That means in an outlook, if we consider outlook as a parameter, we're getting better information gain compared to the windy one. Similarly, in case of humidity, the calculation of information gain as per the formula gives us 0.15. So that is again better than your windy, but still less than your outlook. So outlook is the one. Similarly, we take temperature as well, but still has a very low value. So outlook is the one which gives us a very good information. That is why we have chosen outlook as a measure to start with a decision tree, right? Because we're getting the maximum information gain. Now let's come back to the last topic called confusion matrix. So confusion matrix is again a very straightforward method to calculate the performance of an algorithm, and basically that is classification algorithm. It's used pretty heavily, and it works on the concept of true positive, true negative, false positive, and false negative. Let's try to understand confusion matrix with a simple example. Now here what we are doing, we are having information about 165 cases of patients. Out of 165, 105 have the disease and 60 patients do not have the disease. And the classifier predicted 110 times as yes and no as 155 times. So now we have to come up with the measure of the performance of this algorithm or the model that you have fit for that. So we'll try to create a matrix of yes, true positive, true negative, false positive, and false negative. That means when it is predicted no and there is actual no, how many cases that we have done that? Which is 50. When there is predicted yes, but there is an actual no, that means 10 times. When there is an actually yes and we predicted no, we made it like 5 times. And there is an actual yes and we predicted yes, that is 100. So we create a matrix, something like matrix structure. And we call those matrix values with predicted and expected values based on our prediction is correct or wrong. So if we talk about the true positive, that means there are cases where we have predicted yes and it was actually yes. That means we have predicted that yes, they have disease and they actually have disease. Then we have true negative when we have predicted as they don't have disease and which is the true and they actually don't have disease. When there's a false positive when we predicted that yes, they have disease but they actually don't have disease. That is an error or mistake we did. Then we have false negative, we predicted no. Actually, they do have disease, right? So that is another way around. We again made an error in that case. So based on all those calculation values of true negative and false positive, false negative, we come up with the two terms called sensitivity and specificity. If you see, these are the terms that we talk about, right? True negative is nothing but a predicted no and actual no. True positive is predicted yes and actual yes, like that. We divide it into some kind of matrix form. And then we calculate the sensitivity is nothing but probability of detection of some fields, that is measure of the positive, right, which is nothing but true positive divided by the combination of true positive and false negative. Okay, and that means it gives you a fraction of all those with the disease who get a positive result. Similarly, specificity gives information about the true negatives, right, which is nothing but true negative and the false negative, false positive, and you get some value of that. It will give you a fraction of those without disease. So basically, while doing all this, we get some of the additional information, because if you go with the other accuracy measures where we just calculate the error and we see how many of them is predicted correct and how many of them are predicted wrong. Instead of getting those accuracy measures with confusion matrix, you will get an additional benefit of seeing the behavior of your model. How many of them are predicted correctly? How many of them predicted wrong? How many of them are original correct but your algorithm predicted wrong? How many of them original wrong but your algorithm predicted right? Like that. With the help of these terminologies, you can drill down to the further level. So summary is that in this whole session, we talked about different data types. So let me summarize it. So broadly, it is divided into two types. One is called as quantitative, another is qualitative. And then qualitative is further divided into nominal and ordinal type. Quantitative further divided into discrete and continuous type. Then we have a population of the sample. Population is the whole data set that we're talking about. Sample is just some of the values taken from that, and that too based on some of the techniques. So we talked about the population, probability sampling technique, and non-probability sampling technique. Probability sampling technique can be further divided into random sampling, stratified sampling, and systematic sampling. Non-probability can be further divided into convenience sampling, judgmental sampling, snowball sampling, right? And there is one more sampling technique that I forgot. And then we have a representation of the numerical data, which is nothing but the measure of the center, measure of the spread, and then at the end, very important topics of information gain and entropy. I hope you got information related to that. Thanks a lot for your time. Take care. See you next time. Bye-bye.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!